James Webb may have just found the hidden thing that holds our entire universe together. And if that's true, everything you thought you knew about space is about to feel very, very small. But before we continue, please subscribe to the channel to give your support. Let's continue. You've heard the basic story. The universe is expanding, galaxies are moving away from each other, space itself is stretching. That part is fine. The problem starts when you sit down and add up what's actually doing the pulling. You count all the stars, all the gas, all the planets, every atom that emits or reflects light. You turn that into an energy budget, and you get a brutal result. All that visible matter is only about 5% of what's out there. 5% is the stuff you can see and touch. The other 95% does not show up directly in any telescope, but it clearly affects how things move. On paper, with only that 5%, the universe should be much more fragile than it is. Galaxies should not stay bound so easily. Clusters of galaxies should fall apart over billions of years. The large-scale pattern of structures we map across billions of light years should be much weaker. The equations of gravity say, with only the matter you see, the universe should be losing its grip. But when you actually observe the sky, that is not what you see. So you're forced into the first big question. What is providing the extra gravity that keeps everything from just drifting apart? The most obvious place to look for this missing glue is in how galaxies and clusters behave, because those systems are like stress tests for gravity. In a spiral galaxy, stars orbit the center at huge speeds. Out near the edge, many of them are moving at hundreds of kilometers per second, over 600,000 kilometers per hour, something like 400,000 miles per hour. If only the visible stars and gas were there, those outer stars should not be held tightly enough. They should slowly escape into intergalactic space. Instead, they stay in stable orbits. When astronomers measured those rotation speeds and compare them with the amount of visible mass, they find a mismatch so large you cannot fix it by saying, "We miscounted a few dim stars." You need several times more mass than what you see. The same story appears in galaxy clusters. Galaxies inside a cluster move at hundreds or even over 1,000 kilometers per second, while the hot gas between them glows in X-rays. You can weigh the cluster in different ways, and every method says the same thing. Most of the mass is dark, not emitting light. So you end up with a very direct statement. There is unseen mass behaving like a kind of gravitational glue holding stars inside galaxies and galaxies inside clusters. If that glue is so important, you then need a way to study it in detail, not just indirectly at the edges of what older instruments could do. To push further, astronomers did something extreme. They built a telescope that doesn't sit on a mountaintop, it lives in deep space. The James Webb Space Telescope orbits around a point called L2, about 1.5 million kilometers from Earth, roughly 1 million miles away, where the gravity of the Earth and the Sun balance in a useful way. It has a segmented mirror 6.5 meters across, around 21 feet, coated in gold to work well with infrared light. The whole system is kept extremely cold, about 40 degrees above absolute zero, around minus 233 Celsius or minus 387 Fahrenheit, with some instruments even colder. The reason for that harsh setup is very simple. The universe's earliest light has been stretched by expansion into the infrared, and anything warm on the telescope itself would swamp that faint signal. Webb is tuned to see wavelengths from about 0.6 to roughly 28 micrometers, a full range of near and mid-infrared that earlier telescopes, like Hubble, could only touch the edge of. Its mission is to see the first generations of galaxies, measure their distances and chemical fingerprints, and map how structures grow over cosmic time. In other words, it is designed to watch the skeleton of the universe assemble. Once Webb started sending back data, something larger than just pretty images appeared in the numbers. The telescope did not find a single glowing object labeled "This holds everything together." Instead, the data support a picture where the universe's mass, especially the dark part, is arranged in a connected pattern, a web of high-density regions and low-density voids. When you map where galaxies sit in 3 dimensions, especially very far ones, you don't see a random scatter. You see threads, intersections, and empty gaps. The galaxies line up along these threads because they are tracing deeper wells of gravity formed mostly by dark matter. So the object people talk about here is not a ball or a block. It's this entire connected structure. Dark matter plus ordinary matter falling into it, plus gravity itself behave together like one continuous universe-spanning framework. It dictates where gas can cool, where stars form, where galaxies grow, and where big clusters will eventually sit. Webb's infrared reach and sharp resolution let you see this framework at much earlier times than before. You're catching the pattern when the universe is still young, so you can't just shrug and say, maybe it slowly appeared later. It is already there, doing its job. That leads directly into the next problem. What if the standard story we use to explain that framework is missing something crucial? Right now, cosmology leans on a model called lambda cold dark matter, usually written as LCDM. In simple language, lambda stands for dark energy, a kind of built-in push in space-time that accelerates the expansion of the universe on the largest scales. Cold dark matter is the invisible mass that clumps and forms the skeleton. Add in ordinary matter, the atoms that make stars and planets, and you get a recipe that, before Webb, matched a lot of different observations at once, from the cosmic microwave background to large-scale galaxy surveys. Webb's early deep observations, though, started to stress that model. You now see galaxies that look too massive, too bright, and too chemically evolved only a few 100 million years after the Big Bang. You see evidence that significant structure, the very framework you're calling the universe's glue, is already in place early. If dark matter and dark energy behave exactly the way LCDM assumes, forming those structures fast enough is hard without pushing the model to its limits or beyond. So the stakes are high. If the glue does not act like simple, cold, collisionless particles inside an unchanging dark energy background, you might have to adjust the properties of dark matter, change how dark energy works, or even question whether gravity itself follows Einstein's equations on the largest scales. You're no longer just refining details, you're asking if the entire architecture of the universe has been misread. That naturally sets up the next question you need to answer. How is James Webb able to see this hidden structure and these early, challenging galaxies at all when every earlier telescope either missed them or only hinted at them? Why can this one telescope, sitting a million miles from you, see the hidden structure of the universe when every earlier one basically hit a wall? The first reason is simple but brutal. The light you care about is not the kind your eyes see. The earliest galaxies did not send you red and blue light. They sent harsh ultraviolet and bright visible light. Over more than 13 billion years, the expansion of space has stretched those wavelengths, pulling them out into the infrared. So when you look with Webb, you're not just looking far away, you're looking back in time at light that has been stretched for most of the age of the universe. Webb's instruments, mainly NIRCam and MIRI, are built for exactly that kind of light. They pick up wavelengths from about 0.6 micrometers, just beyond deep red, all the way out to about 28 micrometers, far into the mid-infrared. Your eyes stop around 0.7 micrometers. Hubble mostly operated below about 2 micrometers. Webb keeps going, and that extra range is what lets it see galaxies with more than 13.5 billion years of look-back time, where the universe is only a few 100 million years old. So when you see a tiny red smudge in a Webb deep field, you're not just seeing a faint object. You're seeing light that left when there were no planets like Earth, no Milky Way as you know it, no heavy elements in any serious amount. The color is not a simple "it's red." It is a sign that the wavelength has been stretched by expansion, which tells you the redshift, which tells you the age. The telescope is basically turning cosmic redshift into a time label. That is why infrared matters so much here. Without it, those early galaxies are either invisible or badly misread, and the cosmic skeleton you're trying to trace stays blurry. But just seeing the right wavelengths is not enough. The next question is, how sharp is your view when the thing you want to resolve is billions of light years away? This is where the size of Webb's mirror becomes brutal hardware advantage. The mirror is 6.5 meters across, about 21 feet, made of 18 hexagonal segments working as one surface. The bigger the mirror, the finer the details you can resolve on the sky. That's basic diffraction physics. With that size, Webb can pick out structures only a few hundred parsecs wide inside galaxies billions of light years away. A parsec is about 3.26 light years, and 1 light year is about 9.46 trillion meters, or roughly 5.88 trillion miles. So you're talking about being able to separate features that are a few hundred to maybe 1,000 light years across at distances where the light has been traveling almost the entire age of the universe. In practical terms, that means you can see how clumpy or smooth a young galaxy is, whether it has a compact core, whether star-forming regions are spread out, or whether small companions are merging into it. You're not just seeing a blob, you're resolving structure, and that structure tells you how fast matter is falling into dark halos, how quickly stars are forming, how early the skeleton of the universe was capable of building real systems. Without that resolution, you would just have a few pixels of fuzz, and all the interesting physics would be hidden inside a smear. Now, seeing faint infrared light with that kind of sharpness raises a tough engineering problem. How do you keep the telescope from blinding itself with its own heat? Everything with a temperature emits infrared radiation, including the telescope. If the mirror and instruments were at room temperature, they would glow strongly in the same wavelengths you're trying to measure from distant galaxies. Webb solves this by operating extremely cold. The main mirror sits at around 40 Kelvin. That's about minus 233 degrees Celsius, or minus 387 Fahrenheit. Some of the mid-infrared detectors are cooled even farther down, using a cryocooler system. At those temperatures, the thermal noise, the random infrared glow from the hardware itself, is drastically reduced. What is left in the detectors is dominated by real cosmic signals, the faint warmth of dust and gas lit by young stars, and the stretched-out light from ancient galaxies riding on top of the dark matter framework. So when you see a Webb image full of faint red and orange galaxies, remember that you're not just looking at pretty colors. You're looking at measurements that depended on suppressing the telescope's own heat to almost nothing. That's the only way you can trust that the glow you record really belongs to the universe, and not to a warm mirror or a hot instrument. Without that, the earliest structures would be buried in noise, and the glue you're trying to study would be practically invisible. But you still have a problem. Pictures alone do not tell you distances, speeds, or detailed composition. How do you turn those tiny infrared smudges into hard numbers about how far away they are, what they're made of, and how fast things are moving? That's where spectroscopy comes in, and Webb's NIR spec instrument is the workhorse for it. Instead of just collecting light and forming an image, NIR spec splits the light from hundreds of sources at once into spectra, basically stretching it out by wavelength. In those spectra, you see emission and absorption lines, narrow features from specific atoms and molecules. The amount those lines are shifted toward longer wavelengths tells you the redshift, which means you get the distance and the cosmic age of the object. The strength of different lines tells you the chemical mix, how much hydrogen, helium, oxygen, carbon, and heavier elements are present. The shape and splitting of lines and small shifts inside them tell you about gas motions and star velocities along the line of sight in kilometers per second. When you combine all that, you get more than just a pretty image with a red color. You get a three-dimensional map with distance, age, chemistry, and internal motion. And here's the key link to the glue. From the motions of stars and gas, you can infer how deep the gravitational well is in each system. If the measured speeds are too high for the visible mass to hold them in, you know there's extra mass, the dark component. So spectroscopy is how Webb turns "this galaxy looks red and small" into "this galaxy sits at this redshift, has this much heavy element content, and must sit in a dark halo of at least this mass." That is how you start to outline the invisible structure directly. Now, you might ask, couldn't ground-based telescopes and Hubble do all this already? Why do you need yet another machine? Ground-based telescopes are powerful. Some have mirrors bigger than Webb's, but they have two major problems. The Earth's atmosphere distorts incoming light, and it absorbs much of the infrared. Adaptive optics can correct some of the blurring, but not for very wide fields, and not perfectly. The atmosphere also glows in the infrared, adding noise and blocks entire wavelength bands. Webb dodged the atmosphere by being in space, and it gave you incredibly sharp images in visible and near ultraviolet light, plus some near infrared. But Hubble's mirror is only about 2.4 meters across, far smaller than Webb's, and its instruments were not built to cover the deep infrared range where the highest redshift galaxies now sit. Webb mixes the advantages. It is in space, so no atmospheric distortion. It is optimized for near and mid-infrared, where the earliest light has been shifted. And it has a much larger mirror. When you combine Webb's infrared images and spectra with Hubble's visible data for the same galaxy cluster, and with ground-based radio or X-ray observations, you get a multi-layer map. The luminous galaxies, the hot gas, and the gravitational lensing distortions all line up. The lensing patterns, the way background galaxies are stretched and multiplied, tell you the total mass distribution, including dark matter. The Webb data sharpen those maps, so the dark matter skeleton in that region stands out more clearly than in older surveys. You can literally see where most of the mass is, even when you cannot see it directly. So now the tension ramps up. If you have a telescope that can see stretched out time in the infrared, resolve tiny structures at absurd distances, suppress its own heat and turn light into precise spectra, what happens when it points all of that power at the very beginning of galaxy formation and finds systems that look like they're decades ahead of schedule? How do you even begin to trust your model of the universe when the first deep look with a new telescope shows galaxies that are basically already grown up in a universe that's still a baby? Right away, Webb started picking out galaxies with redshifts around 14, things like JWST-Z14-0 and MOM-Z14. Redshift 14 means their light left them only about 280 to 290 million years after the Big Bang, when the universe was roughly 2% of its current age. That's very early, and yet these galaxies are not just faint little clouds. They're bright, compact, and already show signs of heavy elements, elements like oxygen and carbon that only form in stars and supernovae. In plain words, by the time you're seeing them, they've already formed stars. Some of those stars have exploded, and the gas has been enriched and recycled. You're not looking at a first spark, you're looking at a system that has history. And that's the shock. The timeline you expect from standard cosmology says, first the universe is a hot plasma, then it cools, then the first stars form, then small clumps of matter merge into bigger ones, and over time you get the sort of galaxies you know today. But here, only a few 100 million years in, Webb is spotting objects that look like they've jumped ahead several steps. So you're forced to ask an uncomfortable question. If galaxies look this evolved this early, what does that say about how fast the underlying structure, the dark matter skeleton, must have formed? The surprise gets louder when you look at the estimated masses of some of these early galaxies. Webb's data suggests candidates at redshifts above 10, even pushing towards 16, that appear to hold up to about 10 billion times the sun's mass in stars. Not total mass, just the stars. That's 10 billion suns worth of normal matter already turned into stars only about 250 to 400 million years after the Big Bang. To understand how extreme that is, think about what needs to happen. First, dark matter has to clump under its own gravity, forming halos. Then gas has to fall into those halos, cool, compress, and turn into stars. Those stars then live and die. Some explode, they enrich the gas with heavier elements, and new generations of stars form. All of that takes time. In standard lambda cold dark matter simulations, you do get early galaxies, but building up 10 billion solar masses of stars that quickly usually requires pushing the model very hard, making star formation extremely efficient or starting with unusually large initial clumps. So when Webb shows you several of these too massive, too early objects, it's not just an odd outlier. It starts to look like a pattern. And that pattern raises attention because if your model needs to be stretched this far to fit the data, maybe the model is missing something fundamental about how the glue of the universe works. That brings you straight to the engine room of this problem, the dark matter halos that host these galaxies. If you see 10 billion solar masses in stars, the total mass of the halo has to be much larger because not all gas turns into stars, and not all matter is normal matter. In many galaxies, stars are only a small fraction of the total mass. So you're probably talking about halos in the range of roughly 100 billion solar masses to maybe a trillion solar masses, already assembled in that tiny early slice of time. For comparison, that's the kind of halo mass you might expect around a small modern galaxy today, not in a universe that's barely out of its initial hot phase. To make those halos that quickly, the early density fluctuations, the initial tiny overdensities in the matter distribution, have to grow very fast. Either the starting conditions were more generous to small scales than you thought, or dark matter clumps and collapses more efficiently than the simplest cold and collisionless picture suggests. So theorists are forced back to the drawing board on details like the power spectrum of initial fluctuations, which describes how much clumpiness you have on different scales, and on the microphysics of dark matter itself. Is it really perfectly cold? Does it interact with itself in subtle ways? Does something about gravity on these scales boost the collapse? None of those questions are comfortable, because each possible fix can collide with other observations that were working well before Webb. Put all of these high redshift findings together and you get what people are starting to call a too early structure problem. Webb isn't just picking out one odd beast. It's seeing multiple bright galaxies at redshifts around 12 to 16 with strong signs of star formation and surprisingly high levels of heavy elements. That means several different regions of the early universe managed to build complex systems in a very short amount of time. This directly challenges the clean story where structure slowly ramps up. Instead of a gentle, gradual build where you ease into mature galaxies, it looks more like a sudden jump. The universe goes from almost no structure to serious galaxies exist in what, on cosmic terms, is a blink. If that's true, then whatever is gluing matter together, whatever's shaping these dark matter wells, has to be active and efficient very early on. It doesn't have billions of years to get going. It has a few hundred million. That leads to a sharper, more troubling conclusion about the skeleton itself. The object holding the universe together, this large-scale framework made of dark matter and gravity, might not be a slow construction project at all. It may have snapped into its basic shape very quickly after the Big Bang, laying down deep gravitational wells early on so that gas could slam into them and form stars and galaxies at high speed. In other words, the Webb might have gone from almost nothing to ready to build galaxies in far less time than many pre-Webb models assumed. If that's what the data keeps saying, then you're not just adjusting a few numbers. You're being told that the scaffolding of the universe is more aggressive, more tightly organized, and more efficient than you thought. And once you accept that, the next question gets even more intense. If the skeleton appeared this fast, can Webb catch it in the act of stretching out into full cosmic filaments and threads while the universe is still under 1 billion years old? What does it actually mean for your picture of the universe when you stop seeing single galaxies and start seeing them lined up in a single massive thread, less than 1 billion years after the Big Bang? With Webb, astronomers found exactly that. A chain of about 10 galaxies, all setting at roughly the same redshift, around 5.4, all stretched out along a common line in space. The length of that line is about 3 million light years. In metric terms, that's roughly 2.8 times 10 to the 22 meters, which is on the order of 30 trillion kilometers. In miles, you're talking about around 18 trillion miles. This is not just a small local group huddled together. This is a proper filament, a piece of the early cosmic web, seen when the universe was only about 830 million years old. At that age, the universe is still under 10% of its current age, yet you already see galaxies not just existing, but arranged in a large-scale structure. They're not scattered, they trace a thread. Each of those galaxies is forming stars, building mass, and all of them are sitting inside a shared dark matter structure that runs for millions of light years. When you look at the positions and redshifts, you're not looking at a coincidence. You're looking at a sign that the gravitational skeleton, the object holding matter together, has already organized space into lanes. So here's the next question. If you have a 3 million light year thread like that, what's sitting at the center that makes the whole thing even more extreme? Right along the spine of this filament sits a quasar, a galaxy whose central supermassive black hole is feeding so aggressively that it outshines the galaxy itself. That black hole is not small. You're likely talking about hundreds of millions of solar masses in a single compact object. Matter is falling in at a huge rate, heating up and blasting out radiation across a wide range of energies. Gravitationally, that thing is a deep pit in space-time. Gas from the surrounding filament can fall toward it, funneled along the dark matter structure. As it does, it feeds both the growth of the black hole and the growth of the host galaxy. The whole system behaves like a seed of a future massive cluster, something that might, billions of years later, look like a structure on the scale of the Coma cluster, with hundreds or thousands of galaxies bound together over tens of millions of light years. So now you're not just seeing early galaxies, you're seeing an early cluster in the making, with a monster black hole nailed into its center, and everything else sliding down toward it along the dark matter thread. That's a very direct, physical picture of how the skeleton of the universe drives where big structures will appear. But you might ask, is this really new, or is it just confirming something simulations have been telling you for years? For decades, cosmological simulations have predicted that dark matter should not just clump into isolated blobs. Instead, it should form a web, with filaments connecting dense nodes and large underdense voids in between. Baryons, the normal matter, are supposed to fall into that web, forming galaxies along filaments and big clusters at intersections. That's the standard story. The difference now is that Webb is catching structures that look like those simulated filaments at earlier times, and sometimes at a higher level of development than many models assumed. You're no longer just looking at the late-time Webb mapped by surveys of nearby galaxies. You're seeing a filament at redshift 5.4, with a quasar already acting as a node. You're seeing multiple systems that match the geometry and connectivity expected from the dark matter web. So the idea of a cosmic web is not staying in a simulation box on someone's computer. It's showing up in hard data, and earlier than is comfortable for the slow-built picture. That naturally raises the next issue. If dark matter and galaxies are lining up into threads like this, what about the gas in between? Can you actually measure the stuff filling those filaments directly? Astronomers are starting to push on that. The plan, and in some cases the early reality, is to use emission lines like hydrogen's H-alpha line to trace a diffuse gas. For filaments that are several co-moving megaparsecs long, and 1 megaparsec is about 3.26 million light-years, the average gas density is incredibly low, just a few atoms per cubic meter. That sounds like almost nothing, and compared to air in this room, it is essentially a vacuum. But stretch that density over tens of millions of light years, and you get a lot of mass. Webb's infrared sensitivity lets you pick up faint emission from this gas, especially when it's being lit or heated by nearby galaxies and quasars. From that, you start to estimate not just where the gas is, but how it flows, whether it's streaming along the filament into the central quasar or being pushed back out by feedback. On these scales, the gas follows the underlying dark matter potential. So mapping the gas is another way of tracing the shape of the invisible skeleton. So at this point, what are you really looking at when you say the object that holds the universe together? By now, it's not just a vague idea that there must be extra mass somewhere. You are seeing a three-dimensional structure with specific geometry, length, orientation, and internal dynamics. It is a web-like skeleton, made of dark matter and threaded with gas, running for millions of light years, guiding galaxies into place. If you tried to compare its size in a simple way, you'd say that one strand can be longer than 10,000 Milky Ways laid end to end. But the important part is not the metaphor, it's the control. This structure decides where stars, galaxies, and clusters can form and where they cannot. The object is now a concrete framework with measurable positions, lengths, and densities, not just a placeholder in an equation. And that pushes the tension up another level. Because if you can see the geometry of the skeleton this clearly, the next logical step is to ask, can you also weigh it and map it, even where there are no galaxies at all, just by watching how it bends light? You're looking straight at a galaxy cluster, thousands of galaxies in one field of view. And here's the uncomfortable fact. Most of what's really there is completely invisible to you. Yet you can still draw a map of it. You can't see dark matter directly. It doesn't glow, it doesn't reflect, it doesn't care about your telescopes. But it does one thing perfectly. It bends space-time, and that bends light. When a massive cluster sits between you and even more distant background galaxies, its total mass, including dark matter, warps the path of their light. To your eyes and to Webb and Hubble, those background galaxies look stretched, squashed, and sometimes copied into long arcs and multiple images wrapped around the cluster. That effect is called gravitational lensing, and it turns a galaxy cluster into a kind of natural X-ray machine for mass. You measure how strong the distortions are, how far the arcs are from the center, how many copies of the same background galaxy you see, and in what positions. Then you run the physics backwards. You ask, what mass distribution would bend the light exactly this way? The answer is a detailed mass map, not just of the bright galaxies and hot gas, but of everything that has gravity, including the dark matter. So with lensing, Webb and Hubble together let you see something that emits no light at all, just by watching how it sculpts the view of galaxies behind it. And that raises the next hard question. When you look at a violent system where normal matter and dark matter have actually separated, which one really behaves like the glue? One of the cleanest examples comes from systems like the Bullet cluster, where two galaxy clusters have smashed through each other. In those collisions, the stars in each galaxy mostly sail past because they're so far apart. The hot gas clouds, though, collide head-on, slam into each other and slow down. X-ray observatories show that the brightest, hottest gas, the normal matter, is left trailing in the middle region between the two clusters. Now, bring in lensing. When you map the total mass using gravitational lensing, the peaks of the mass distribution don't sit on the hot gas. They line up instead with the galaxies, which have moved ahead. In other words, most of the mass, the dark matter, went straight through the collision with very little friction, while the normal matter got stuck. The glue that holds the cluster's gravity wells together is not mainly the visible gas. Webb's NIR-CAM images act sharper views of the galaxies themselves, especially the faint ones that Hubble struggled with. And NISPR spectra give you precise redshifts and velocities. That lets you cleanly separate which galaxies really belong to each cluster and which ones are just projected in front or behind. When you fold that into the lensing analysis, you get a more accurate mass map, and the same basic picture shows up. The dark matter component has slid ahead, the normal gas has lagged, and gravity is dominated by something you can't see. That separation is devastating for simple maybe gravity just behaves differently on normal matter. If you try to explain all the extra gravity by tweaking how visible matter curves spacetime, you can't easily get a situation where the gravitational mass is in one place and the bulk of the visible matter is somewhere else. The bullet cluster type systems are some of the strongest pieces of evidence that there is genuinely extra stuff, real unseen mass acting as the main glue. As more of these clusters are observed, something else becomes clear. The dark skeleton is not a smooth blob. It has structure, and Webb and Hubble together are now resolving that structure in serious detail. By the mid-2020s, combined data from Webb and Hubble have produced some of the sharpest dark matter maps so far. In those maps, you see dense cores where the cluster centers sit, and fainter bridges of mass connecting them, lower density filaments that link cluster to cluster. When you overlay the positions of luminous galaxies in X-ray gas, you find that ordinary matter broadly traces the same web, but it's the dark matter that defines the clean outline. The galaxies are like lights pinned into a much bigger invisible frame. In some clusters, you can even pick out smaller subclumps of dark matter, tied to infalling groups of galaxies, and the weak lensing signal between big clusters hints at the larger filaments connecting them. So you're not just seeing isolated halos, you're seeing parts of the full cosmic web in projection, with enough resolution to say, here's a node, here's a bridge, here is where the mass thins out. The scales and masses involved are enormous. Typical strong lensing clusters have total masses in the range of about 100 trillion to 1,000 trillion times the sun's mass. That's 10 to the 14 to 10 to the 15 solar masses, spread over a few megaparsecs, where 1 megaparsec is about 3.26 million light years. In kilometers, that's tens of millions of light years across, or roughly 10 to the 23 meters across. If you could somehow compress a cluster like that down to the size of Earth with a radius of about 6,371 kilometers, roughly 3,959 miles, the result would be an object with the mass of millions of trillions of suns, packed into a sphere the size of a planet. The surface gravity would be unimaginable, many orders of magnitude beyond anything we deal with. On that kind of scale, you're dealing with space-time so deeply warped that light itself takes curved paths around it as a normal behavior. Looking at those lensing maps, a pattern jumps out that changes how you think about dark matter. It stops feeling like a loose cloud of individual particles and starts behaving on these scales like a single continuous medium. The maps show smooth regions, ridges and dips, not random speckles. The dark matter distribution looks like a deformed, connected block of invisible material, stretched and squeezed by gravity and cosmic expansion. On the scale of galaxy clusters and filaments, you can treat this dark component as one interconnected object, a universe-sized mass distribution that everything else has to follow. Galaxies orbit inside its wells, gas flows along its ridges, light bends around its peaks. The object holding the universe together isn't a solid in the normal sense, but it acts as a coherent structure, with shape, with internal features, and with a very strong say in where anything can be. And that pushes you straight into the next escalation. If the dark skeleton behaves like one continuous object on large scales, what happens at the sharpest dents in that object, where gravity stops being just strong and becomes extreme, around the biggest black holes in the cosmos? How do you explain a universe that is still under 1 billion years old, but already has black holes so big they look like they skipped the line? Webb has picked out quasars at redshifts above 7, powered by black holes with masses of millions to billions of suns. Redshift 7 means you're seeing them when the universe is under about 800 million years old. At that point, there hasn't been much time to build anything, yet somehow these objects have already eaten enough matter to become giants. Standard growth scenarios, where you start from normal black hole seeds, have a hard time getting you to 1 billion solar masses that quickly, without pushing accretion close to the maximum steady rate almost continuously, or starting with unusually heavy seeds. The gravity around these monsters is extreme. Close to the event horizon, within a few Schwarzschild radii, orbital speeds reach a significant fraction of the speed of light. You're talking tens of thousands of kilometers per second, which is a few percent of c, the speed of light. At those speeds, time runs noticeably slower. Light gets strongly bent, and matter falling in releases huge amounts of energy before crossing the horizon. When Webb looks at these quasars in the infrared, it sees the hot gas in the accretion disk and the dust around it glowing across space and time, telling you that supermassive black holes were already a major player while the universe was still very young. So you hit a basic tension. If the dark skeleton is the framework, why are the heaviest gravitational dents, these early black holes, already so deep? There's a second, quieter clue that these black holes are not just random add-ons. In nearby galaxies, there's a tight correlation between the mass of the central black hole and the velocity dispersion of stars in the bulge. Basically, how fast stars are moving around in the central region. That's strange, because the black hole's event horizon is tiny compared to the galaxy, but its mass tracks a property of stars spread out over thousands of light years. The simplest way to read that is the black hole and the galaxy, and by extension its dark matter halo, grow together. Gas falls in along cosmic filaments, feeding star formation in the galaxy and accretion onto the black hole at the same time. When the black hole is very active as a quasar, it launches jets and winds that push back on the surrounding gas, heating it, stirring it, and sometimes blowing it out of the central region. That feedback changes how easily gas can cool and form new stars, and it also changes how gas is distributed in the inner parts of the dark matter halo. Webb's infrared spectroscopy is crucial here, especially at high redshift. NIRSpec lets you split the light from the quasar and its host and measure emission lines from gas moving at hundreds or even thousands of kilometers per second. Those line profiles tell you about outflows, inflows, shocks, and turbulence. You can see where gas is being pulled in toward the black hole and where it is being pushed out in fast winds. Even at redshifts of 6, 7, and 8, you can start to quantify how aggressive this feedback is and how it might be regulating the growth of both the galaxy and the halo. This means the central black hole is not just a passive object sitting at the bottom of a well. It's an active part of the structure, linked to the halo and talking to the rest of the system through radiation and outflows. On the scale of the cosmic web, something similar plays out in a more global way. Where filaments intersect, you get nodes, and those nodes are typically where the biggest halos live. Those biggest halos tend to host the most massive galaxies, and inside those, you often find the most massive black holes. So now the skeleton of the universe is not just a smooth background of dark matter, it has sharp pits driven by black holes that sit at key junctions. The structure is hierarchical, and the black holes are sitting at the control centers. The next layer of this is about energy, because the amount these objects can dump into their environment is not just a small correction, it's on the same scale as the energy needed to hold gas in a galaxy in the first place. Quasar outflows and jets can carry total energies on the order of 10 to the 60th to 10 to the 61 ergs. To translate that, a single supernova is roughly 10 to the 51st ergs. So you're dealing with millions of supernova explosions, all tied to a single active galactic nucleus phase. In more intuitive terms, if you had a billion planets, each with a mass of Earth, and you somehow accelerated all of them to tens of thousands of kilometers per second, that's the kind of energy we're talking about. When that kind of power is dumped into the gas inside a galaxy and its halo, the structure changes. Cold gas can be heated up so it can't easily collapse into new stars. Gas clouds can be blown out into the halo, or even into intergalactic space. Shock waves and turbulence can stir the medium, changing its density and temperature profile. Over time, that feedback can shut down star formation in some regions, while leaving others relatively untouched. In terms of the cosmic web, that means black hole feedback becomes part of the way the object holding the universe together shapes itself. Dark matter sets the basic wells, gravity pulls matter in, but black holes pump energy back out, carving out low-density regions, quenching some galaxies while leaving others active. Parts of the web stay bright and star-forming, others go quiet and red. The distribution of gas, and therefore the visible part of the skeleton, is no longer just a passive response to gravity. It's being sculpted by these compact engines at the centers of halos. So now you have a universe where the invisible skeleton is reinforced by supermassive black holes that grew too fast, too early, and then used their energy output to rewrite the gas distribution sitting on that skeleton. And that leads to a sharper question. If black holes and dark matter halos are already this active and connected, what happens when you zoom back out to even larger scales, where whole galaxy clusters sit on twisting, rotating filaments of the web itself? How do you know the cosmic web isn't just a frozen pattern on the largest scales, but a living structure that's still pulling, squeezing, and even spinning entire regions of the universe? As the universe ages, the dark matter filaments you've been hearing about don't stop doing their job. They keep feeding material into massive galaxy clusters sitting on their intersections. Gas flows along the threads, galaxies fall in, and clusters grow. Webb's infrared eyes catch galaxies on their way down these filaments into the cluster cores, and the physics of those encounters is anything but gentle. As a galaxy dives into the hot, dense gas that fills a cluster, it feels ram pressure from that gas, like driving into a strong wind. Gas gets stripped out of its disk. You see long tails of material trailing behind, and in some cases, that compression triggers short, violent bursts of star formation. Cluster diameters easily reach several megaparsecs, tens of millions of light years across, and all along the edges and infall regions, Webb is picking up signatures of galaxies getting torn up and reshaped by the environment. Clusters are not static piles of galaxies, they are active nodes in the web, still being fed. So you have these huge clusters sitting on filaments, getting bigger over billions of years, and that naturally raises the next question. Are the threads themselves just simple streams, or are they doing something more dynamic? Radio observations gave a surprising answer. Using the Meerkat radio telescope, astronomers found a filament about 50 million light-years long, containing hundreds of galaxies and a lot of dark matter that is actually rotating as a whole. 50 million light-years is on the order of 4.7 times 10 to the 23 meters, a ridiculous distance on human scales, and yet the entire structure shows coherent rotation, with typical speeds around 396,000 kilometers per hour, about 246,000 miles per hour. This isn't a small whirlpool. This is a chunk of the cosmic web, tens of millions of light-years long, turning. That takes the idea of the skeleton to another level. The web isn't just sitting there frozen in a pattern. It's dynamically twisting, exchanging angular momentum, and dragging galaxies along. When you drop a galaxy into that environment, you're not just dropping it down a hill, you're adding it into a rotating, shearing flow that exists on the scale of hundreds of millions of trillions of kilometers. Now, if radio telescopes can show you that kind of bulk motion in one filament, what happens when you combine that with Webb's precise distance measurement along these structures? Webb gives you very accurate redshifts for galaxies all along a filament, not just the rough, these are all about the same distance. Tiny differences in redshift, once you correct for the overall cosmic expansion, tell you about peculiar velocities, the extra motions on top of the Hubble flow. You can see where galaxies are flowing inward along a filament toward a cluster center, where gas and galaxies might be shooting back out in feedback-driven outflows, and where there's shear or rotation across a structure. Put together with radio data and other surveys, you start getting a kinematic map, not just a static map of the cosmic web. On scales of tens of megaparsecs, beyond the size of individual superclusters, you're seeing inflows, outflows, and twists. The skeleton you've been treating as an object is flexing, and that flexing has real consequences for how halos merge, how clusters assemble, and how galaxies are oriented and spun up. The key question then becomes, how does gravity manage to organize motion on scales this big, when the average density in the universe is so low? Across a distance of 50 million light-years, that's roughly 4.7 times 10 to the 23 meters, the average density of matter in a filament is only slightly higher than the mean density of the universe. You're talking about a few times the cosmic average, which is already incredibly thin, much emptier than any vacuum chamber on Earth. But when you add up that small excess density over such a vast volume, you get a huge total mass. That mass, acting through gravity over billions of years, is enough to induce coherent motions at hundreds of kilometers per second, the kind of speeds that correspond to hundreds of thousands of kilometers per hour. So this is gravity doing exactly what it does best, very weakly at any one point, but relentlessly over absurd distances and timescales. The result is a filament that not only funnels material into clusters, but also rotates as a single connected structure. That's your object that holds the universe together, literally turning in space, not as a metaphor, but as a measurable dynamic behavior. And once you realize the web is both holding matter together and still moving and twisting, you run into an even bigger tension. If gravity and dark matter are building and spinning the skeleton, what's the thing that's trying to tear it all apart faster and faster on the very largest scales? How do you make sense of a universe where one invisible component is pulling everything together while another invisible component is pushing everything apart faster and faster? On one side, you have dark matter and normal matter, slowly building the skeleton, collapsing into halos, forming filaments, feeding clusters. On the other, you have dark energy, which does the exact opposite. Dark energy is not a local force. It doesn't push galaxies like a wind. It's built into space-time itself. On scales of hundreds of megaparsecs, hundreds of millions of light-years, it dominates the energy budget. The result is that the expansion of the universe is not just ongoing, it's accelerating. Galaxies that are far enough apart aren't just drifting away. Their separation is increasing at an ever-growing rate. So you end up with this weird split, gravity and dark matter trying to tighten the web, dark energy trying to stretch the whole fabric under it. So then you have to ask, where exactly does Webb fit into this fight between pull and push? Webb is not just a pretty picture machine, it's part of the precision toolbox for measuring the expansion history. When you observe galaxies and supernovae at high redshift, you're not only getting a snapshot of what they look like, you're getting distances and ages. By combining Webb's infrared observations with redshift data, you pin down how bright certain standard candles really are, and how far away they must be to look as faint as they do. That feeds into the cosmic distance ladder, the chain of methods we use to convert redshift into distance. Once you have a lot of these measurements across different redshifts, you start charting how the expansion rate has changed over time. Combine that with signals from the cosmic microwave background and with large galaxy surveys, and you can constrain the equation of state of dark energy, basically how its pressure relates to its energy density. If dark energy is a simple cosmological constant, that relation has a fixed value. If it's something more dynamic, like a field that changes over time, that value can drift. Webb's job is to tighten the error bars, especially at earlier times when optical telescopes struggled because the key light was redshifted into the infrared. But this leads to an important practical question. If dark energy is everywhere all the time, why doesn't it rip your own neighborhood apart? On small scales, a few megaparsecs or less, gravity from local mass still wins. Take the Milky Way and Andromeda. They're about 2.5 million light-years apart, roughly 0.77 megaparsecs. On those scales, their mutual gravity is stronger than the tendency of the universe to expand. That's why we are not drifting away from Andromeda. We're moving towards it at about 110 kilometers per second, around 250,000 miles per hour. Our local group of galaxies is gravitationally bound. Dark energy isn't pulling it apart. Stretch out to tens or hundreds of megaparsecs, and the story flips. There, the average density drops. Local gravitational attraction gets weaker, and dark energy's effect on the spacing between galaxy groups becomes dominant. The filaments and clusters are still there, but the space between big structures grows faster than it would in a universe without dark energy. On those scales, the cosmic web is literally being stretched, even as gravity is still working locally inside nodes and along filaments. This sets up a deeper tension that Webb is now making harder to ignore. How do you reconcile a universe that builds structure very quickly early on with a universe that has strong late-time acceleration? If Webb's early galaxy data keep suggesting that massive, evolved systems are already in place a few 100 million years after the Big Bang, you have to check whether the standard dark matter plus constant dark energy picture can really produce that. One option is to change the details of dark matter. Maybe it's not perfectly cold and collisionless. Another is to change how dark energy behaves, especially at early times. Some recent work explores models where dark energy's influence was different in the young universe, or where gravity itself is slightly modified on large scales. Webb doesn't directly measure dark energy, but by locking in the timing and intensity of star formation and structure growth at high redshift, it forces those models to either match reality or be thrown out. If Webb's early galaxy data keep suggesting that massive, evolved systems are already in place a few 100 million years after the Big Bang, you have to check whether the standard dark matter plus constant dark energy picture can really produce that. One option is to change the details of dark matter. Maybe it's not perfectly cold and collisionless. Another is to change how dark energy behaves, especially at early times. Some recent work explores models where dark energy's influence was different in the young universe, or where gravity itself is slightly modified on large scales. Webb doesn't directly measure dark energy, but by locking in the timing and intensity of star formation and structure growth at high redshift, it forces those models to either match reality or be thrown out. Once you accept that the same data that reveal the glue also question how long the glue can keep working, the pressure increases again, because you're led to an even sharper possibility. What if the problem isn't just about dark matter or dark energy? What if the basic rulebook of gravity itself is different on these scales than what Einstein wrote down? How do you know the problem is really missing stuff, and not that the basic rulebook of gravity itself is off? Just enough to fool you on the biggest scales. Looking at Webb's early galaxy results, some researchers don't stop at "we need more dark matter" or "we need weird dark energy." They push one step further and say maybe the way space-time responds to matter and energy is slightly different from Einstein's equations when you go to very low densities or very large distances. In other words, maybe gravity itself changes character out there. These are modified gravity models. Instead of adding tons of unseen particles, they tweak the law, trying to reproduce what you see: galaxy rotation curves, gravitational lensing, and large-scale structure, with less dark matter, or in some cases, almost none. On paper, that sounds attractive. One big change instead of two invisible components. But there's a catch. You can't just change gravity in one place. If you modify how it works to fix galaxy rotation speeds, that same modification will affect how galaxy clusters lens light, how structures grow over billions of years, and how the cosmic microwave background looks. Everything is tied together. So as soon as you write down a modified gravity theory, the universe hits you with a scorecard of tests, and Webb is adding some of the toughest ones. So the next step is obvious. Can you actually tell from Webb's data whether gravity is allowed to be different like that? Webb gives you two major lines of attack. First, its high-resolution lensing data, especially when combined with Hubble, shows you how mass bends light in detail, in clusters and around galaxies. Second, its maps of galaxy clustering at different redshifts tell you how fast small density bumps in the matter distribution sharpen over time. That's the growth rate of structure. Different gravity laws predict different histories for that growth. If gravity is stronger or weaker than general relativity on large scales, or behaves differently in low-density regions than in high-density ones, the pattern of lensing and the rate at which filaments and clusters come together will change. You might get too much lensing for a given amount of visible and dark matter, or not enough. Structures might form too fast or too slow compared to what you see in Webb's early galaxies and their environments. By comparing the predicted growth curves from these modified models to the actual data Webb is assembling, you can start ruling out entire families of theories. A model that looked fine against a limited dataset can fail badly once you add precise high-Z galaxy clustering and lensing from Webb into the mix. So Webb isn't just telling you something is weird. It's helping you kill off bad explanations. But there's a more technical question here that matters a lot. How do you even write down gravity behaves differently in a way you can test without drowning in equations? One way cosmologists do it is with a parametrization that separates how matter and light feel gravity. You can think of it as introducing two functions, usually called something like mu and sigma, that act as multipliers. One modifies how strongly matter responds to gravity, affecting how structures grow. The other modifies how light is deflected, affecting lensing. You're not changing the whole theory in one wild step. You're introducing controlled knobs that say, okay, if gravity is slightly stronger here, or light bends slightly more there, what happens? Then you feed in data. The cosmic microwave background gives you constraints from the early universe. Galaxy surveys and redshift space distortions tell you about structure growth at intermediate times. Lensing measurements, including those from Webb looking at distant clusters and galaxies, tell you about how light is bent at different redshifts. By combining all of these, you can start putting limits on how far mu and sigma are allowed to drift from their general relativity values. So far, when you fold in everything, the allowed deviations are small. Gravity, at least at the level these tests can see, looks very close to what Einstein wrote down. That doesn't mean all modified gravity ideas are dead, but it does mean any viable version has to be very subtle, hiding in corners that are hard to probe, not doing anything dramatic that would easily solve all the early structure tension by itself. And that brings you to a sharp twist in the story, because it changes how you talk about the object holding the universe together. Up to now, you've mostly treated that object as a dark matter skeleton, plus gas and galaxies, sitting inside ordinary general relativity. But if you leave the door even slightly open to modified gravity, there's another way to frame it. The object might not be a thing made of particles or fields at all. It might be the law itself, the shape of spacetime's response to energy and mass. In that view, what Webb is really testing is whether the rule book bends. The dark matter web, the filaments, the clusters, the lensing maps, and the early galaxies are all stress tests. You push gravity into regimes of low density, high redshift, and large scale, and you see if it cracks. So far, the cracks are small and hard to interpret. Webb's early galaxies say something is too fast, too early. The precision lensing and growth data say gravity can't be wildly different, or everything else breaks. You're left in a tight spot. The object that holds the universe together might still be dark matter, plus standard gravity. It might involve a small twist in gravity's behavior that only shows at certain times or scales, or it might be a more complex mix of both. But either way, what Webb is doing is forcing you to stop hand-waving. The cosmic skeleton is no longer just a simple particle problem or a simple geometry problem. It's starting to look like a layered system where dark matter, gravity, and normal matter all interact. And that leads you straight into the next level of detail, because even if you keep general relativity and dark matter, you still haven't accounted for all the visible structure sitting on that skeleton. The gas streams, the star-forming filaments, and the magnetic fields that thread through all of it. If the dark matter skeleton is the frame, what exactly is all the normal stuff doing on top of it? Just sitting there, or actually changing how the web behaves? Even if dark matter carries most of the mass, it's the normal matter, the baryons, that you actually see. And those baryons are mostly gas. Webb is extremely good at tracking that gas, not in the X-ray hot phase, but in the warm and dusty phase that glows in the infrared. In deep fields and in structures around clusters and filaments, Webb picks up emission lines from elements like hydrogen, oxygen, and carbon, and also smooth infrared light from dust grains warmed by starlight. When you stack those detections across many galaxies, you see that gas isn't sitting in random blobs. It sits in filaments that line up with the dark matter structure, acting like highways that move material in toward galaxies. Where two or more streams intersect, you often get a spike in star formation. Gas is compressed, cools more efficiently, and collapses into new stars. Webb sees this in the infrared as strong emission from young, hot stars and the dust around them. Those intersections are where the skeleton gets lit up. The web isn't just a passive scaffold with gas sprinkled on it. The gas flows along specific paths, slams into nodes, and triggers real events. Starbursts, active galactic nuclei turning on, and the rapid buildup of stellar mass. So, if the gas is already acting like a delivery system along the skeleton, how early does that start? Some of the more aggressive analyses of Webb data point to significant star formation already happening at redshifts around 12 to 17, which corresponds to roughly 200 to 400 million years after the Big Bang. That's extremely early. At those times, you're only just out of the so-called cosmic dark ages, when there were no stars and no galaxies as we know them. And yet, the infrared data hint that gas has already found the dark matter wells, collapsed along the filaments, and started turning into stars at a meaningful rate. That means the baryonic part of the web, the gas, is lighting up the skeleton very early. You're not waiting a billion years for the first significant star-forming structures. You're seeing them a few 100 million years in. That fits with the too early galaxy story and reinforces it, because you're not just counting galaxies, you're seeing the fuel lines that fed them. The web is acting like a network of pipelines, and those pipelines were open for business fast. At that point, you might think the story is just gravity and cooling. Gas falls in, cools, forms stars, repeat. But on top of that, there's another layer you can't see directly that still affects how gas moves: magnetic fields and turbulence. On galactic and cluster scales, the gas is threaded by magnetic fields with strengths on the order of microgausses. That's a few millions of a Tesla. In a lab, that looks tiny, but spread over kiloparsecs, thousands of light years, it matters. Charged particles spiral around magnetic field lines, and gas that's partly ionized feels forces from those fields. Turbulent motions in the gas twist and stretch the field lines, and the fields push back. This magnetic tension helps guide gas along certain directions and resist motion in others. So now, gas flowing along a filament isn't just feeling gravity and pressure, it's also feeling magnetic structure. On large scales, that can help keep flows collimated, focused along the filament, and influence how easily gas can fall into a galaxy versus being deflected into the surrounding medium. You get a feedback loop. Gravity pulls gas in, turbulence stirs it, magnetic fields channel it. The net effect is another layer of glue, not in the sense of extra mass, but in the sense of extra structure that shapes the paths gas can take across the skeleton. But the baryonic web isn't just being fed, it's being carved up and heated by violent events inside galaxies themselves, and Webb can actually see those scars. Every time stars form, some of them end as supernovae, injecting energy and heavy elements into the surrounding gas. Active galactic nuclei powered by accreting black holes can launch winds and jets that punch straight out of the galaxy's disk. Webb spectroscopy picks up outflow signatures at a few hundred kilometers per second, sometimes more, in lines from ionized gas. Speeds of, say, 300 kilometers per second means that, in principle, a parcel of gas could cross the Earth-Moon distance, about 384,400 kilometers, in just over 20 minutes. That's the kind of velocity we're talking about, but applied not to a spacecraft, to huge clouds of gas. Over millions and billions of years, those outflows matter. They can blow holes in the gas disk, vent material into the halo, and even push gas out into intergalactic space, where it can cool and later fall back along filaments. They also heat the gas, making it harder to collapse again immediately. So, feedback from supernovae and active galactic nuclei literally sculpt the baryonic web. It can thin out some filaments, making them more transparent and less star-forming, while concentrating gas in others. Webb lets you measure where gas is leaving galaxies, how fast it's moving, and how much mass is involved, especially at high redshift, where previous telescopes simply didn't have the reach in wavelength or sensitivity. Put all of this together and the picture changes again. The object that holds the universe together is no longer just dark matter plus gravity. On top of that, you have a complex, evolving baryonic web, gas flowing along filaments, turning into stars, getting blown out, interacting with magnetic fields, and slowly reshaping itself in response to internal feedback. The visible universe is a dynamic skin on a relatively smooth, dark skeleton, and that skin is full of shocks, flows, and structural changes. And that leads to another pressure point. Because once you see how complicated the baryonic layer really is, you have to ask, do our best simulations built on lambda CDM actually reproduce what Webb is seeing, or are they starting to crack under the load of all this new data? How do you trust the model of the universe that nails almost every test, except the one your newest, sharpest telescope cares about most? For years, lambda cold dark matter has been the workhorse. You plug in dark matter, dark energy, and normal matter with the right ratios, and the simulations do really well. They reproduce the tiny temperature ripples in the cosmic microwave background. They match the large-scale distribution of galaxies over hundreds of megaparsecs. They give the right counts of galaxy clusters over time. On paper, it's a big win. Then Webb walks in and drops a problem on the table. Those massive, compact, chemically evolved galaxies only a few 100 million years after the Big Bang. When you overlay Webb's early galaxy data on top of lambda CDM simulations, you start getting a mismatch. Too many big galaxies too early. The simulations can make galaxies, but not that many, not that massive, not that fast, without pushing something to the edge. Suddenly, your standard model is under a stress test it wasn't really built for. So you get to a hard question. Do you throw out the whole thing, or do you try to patch it? One of the first patches people look at is the initial power spectrum of density fluctuations, basically the pattern of tiny over and under densities in the early universe that later grow into structures. In standard lambda CDM, that spectrum has a particular shape, constrained by cosmic microwave background data and other observations. If you boost the power on small scales, you make small dark matter halos form earlier and more easily. That, in principle, could help you build those early massive galaxies Webb is seeing. But there's a big problem. You don't get to change the power spectrum just for Webb. The same initial conditions also set the stage for everything else. The microwave background, the galaxy clustering we see at later times, the lensing statistics. If you crank up small-scale fluctuations enough to fix the too early, too big galaxies, you risk overproducing small structures later on, or messing up the match with precision CMB measurements. It's like trying to fix a crack in one wall of a house and realizing that as soon as you move that beam, the floor, the roof, and the other walls start shifting too. The foundation is shared. So maybe you don't mess with the initial conditions. Maybe you ask a different question. What if the dark matter itself isn't exactly what you assumed? In lambda CDM, dark matter is treated as cold and collisionless. Cold just means its particles move slowly compared to the speed of light in the early universe, so they fall into small structures easily. Collisionless means they barely interact with each other except through gravity. That combination gives you a certain pattern of halo formation and merging. If early galaxies are too massive and too common in Webb's data, you can test alternatives. Maybe dark matter is warm, so it smooths out small structures, or self-interacting, so it behaves a bit more like a fluid, or even composite with internal structure. The problem is, these changes don't just affect when halos form, they also affect how clumpy dark matter is on small scales. Webb, together with other instruments, can probe that clumpiness using fine details in gravitational lensing. For example, in strongly lensed quasars, the brightness ratios of multiple images can be tweaked by small dark matter clumps along the line of sight. If dark matter is too smooth, you get one pattern. If it's very clumpy, you get another. Webb's sharp infrared vision lets you measure those flux ratio anomalies better, tightening the limits on how grainy the dark matter distribution is. So again, any exotic dark matter model that helps you with early galaxies has to pass the lensing tests, the cluster tests, the CMB tests, and the large-scale structure tests. You can't just say, let's make dark matter weird and walk away. Webb is adding new, very specific constraints. If you don't like adjusting the initial fluctuations too much, and you don't want to break dark matter, there's another lever: dark energy. What if lambda, the lambda in lambda CDM, isn't actually a constant? In the simplest picture, dark energy is just a fixed energy density of the vacuum, the same at all times. But there are models where dark energy has a more interesting history. One example is early dark energy, where a dark energy-like component is more important at high redshift in the early universe, and then fades, leaving the late-time acceleration to a different or smaller component. Changing how much effective dark energy you have at early times can impact how fast structures grow. A little more repulsion early could suppress growth. A little less could let structures form faster. Webb's early universe data are one of the few direct ways to test these ideas. By locking down how many massive galaxies exist at, say, redshift 10, 12, 14, and how strong their star formation is, you're effectively measuring how quickly overdense regions grew out of the initial soup. Then you compare that to the growth history predicted by different dark energy models. If early dark energy was strong, maybe you don't get enough early structure. If it was weak or absent, maybe you get too much. And again, you have to satisfy CMB constraints and late-time expansion measurements at the same time. So you end up in a tight balancing act. Tweak the power spectrum too much, and you fail the CMB. Make dark matter too exotic, and you fail small-scale lensing or cluster counts. Change dark energy's behavior, and you risk wrecking the observed expansion history or the CMB peaks. Webb doesn't give you the luxury of sloppy fixes. Its early galaxy census is precise enough that any adjustment has to survive a whole stack of cross-checks. That's why people say the model is creaking rather than collapsing. Lambda CDM still passes a huge number of tests, but Webb has pushed it into a corner where the corrections can't be casual. You're now in a regime where every knob you touch, dark matter properties, dark energy dynamics, initial conditions, gravity itself, has consequences across the whole cosmic history. And that brings up the next high-pressure question in this story. If the simulations are starting to strain, is there any hope that sharper, more detailed images of the cosmic web itself, not just halos and clusters, but the actual gas and galaxies along the filaments, can show you exactly where the model fails first? How do you know the cosmic web you see in simulations is really out there, and not just a nice pattern your computer likes to draw? In 2025, deep observations finally gave you high-definition images of the gaseous web itself, not just the galaxies riding on it. After stacking exposures, stripping out foregrounds, and pushing the data processing hard, astronomers pulled out a faint glow tracing long filaments of gas and denser knots where those filaments meet. You were looking at structures stretching over millions of light years, with gas so thin it's only a few atoms per cubic meter, yet still glowing just enough to be seen. That's the cosmic web in actual photons, not just in code. And that's where Webb comes in as the perfect partner. Those high-definition gas maps tend to sit at moderate redshifts and specific wavelengths. Webb can then zoom in on the same regions at higher redshifts and in the infrared, tracing the galaxies and dust that sit inside those filaments earlier in time. One dataset shows you the gas backbone. Webb shows you the embedded galaxies, their star formation, and their dust content at epochs where the Webb was younger and less evolved. Together, they turn the Webb from a theory into a layered observation. Once you see that structure directly, another question hits. Does the Webb just hold galaxies, or does it actually decide what kind of galaxies they become? Simulations have been hinting for years that galaxy shape and spin know about their environment. Disk galaxies, with nice rotating structures, tend to have their spin axes aligned in specific ways relative to nearby filaments. Spheroidal, more elliptical systems tend to sit in denser knots where filaments intersect, or in the inner regions of clusters. That's the sort of thing you can wave away as maybe until you have enough real data. Now, with large surveys and targeted follow-up, you see strong trends. Galaxy morphology changes with filament density. Thin, rotating disks are more common along the threads. Rounder, puffier systems dominate where the Webb is thickest. Webb helps by pushing that morphology environment link to higher redshifts. In the infrared, it can still resolve the structure of galaxies that are billions of light years away. It tells you whether they're clumpy, disk-like, or already bulge-dominated, and it measures their orientations. When you overlay that on filament maps, you see the same patterns starting early. The Webb isn't just a passive backdrop, it's actively steering how galaxies spin, merge, and thicken. The direction and strength of the filaments matter for the final shape of the objects you see. So if the Webb sets positions and orientations, can you also tie together all three components in one place? The dark skeleton, the gas, and the stars? That's exactly the kind of multi-layer picture Webb is built to deliver. From lensing using Webb plus Hubble, you get dark matter-dominated maps in and around clusters and strong filaments, showing you where most of the mass is. From deep spectroscopy and imaging, you get gas emission lines, tracing the diffuse medium and the denser streams feeding in. And from the same data, you pull out star formation indicators like hydrogen recombination lines and infrared dust emission, telling you where new stars are forming and at what rate. When you stack these layers, you literally see three different views of the same object. The dark matter map outlines the wells and ridges, the basic gravitational shape. The gas maps show how baryons fill those wells and flow along those ridges. The star formation tracers light up the spots where gas is dense and cold enough to collapse. If the dark matter skeleton shifts, the gas distribution follows. If feedback blows gas out of a region, star formation shuts down, even if the dark matter is still there. Webb gives you the ability to check, region by region, whether that chain holds at high redshift the same way it does nearby. The result is that the object that holds the universe together stops being a vague phrase and turns into something you can describe in layers. Dark skeleton, gaseous flesh, stellar skin. Three components, one underlying shape. And when you back up to truly huge distances, hundreds of megaparsecs, something striking happens. All of those different maps start to blur into the same pattern. From far enough away, the details of individual galaxies disappear. What you're left with is the geometry. Whether you're looking at a dark matter distribution from lensing, a gas map from faint emission, or a galaxy catalog from deep imaging, you see the same web, the same network of filaments, sheets, and voids. The tracers change, but the large-scale pattern doesn't. The cosmic web looks like one integrated structure, one connected object in every dataset. That's the key point here. Whatever you choose to map, dark matter, gas, or stars, you are always following the same hidden architecture. The differences are just different faces of the same thing. Webb's role is to lock that in at early times, so you're not just guessing that the pattern was there, you're watching it emerge and sharpen. And once you admit that all these views are just different cross-sections of one gigantic framework, the next question is obvious and sharp. Can Webb's future deep surveys actually chart how that framework fills in over time, slice by slice, until you have a full time lapse of the skeleton being built? How do you actually turn all of this from a few shocking snapshots into a full story of how the cosmic skeleton grew, step by step, over more than 13 billion years? Webb's answer is you stare at tiny pieces of sky for a ridiculous amount of time. Deep field programs stack hundreds of hours of exposure on areas that are sometimes smaller than the size of the moon on the sky. In those deep fields, every faint red blob is a galaxy at some different distance, so each image is really a stack of time slices, from redshift around 1, a universe a few billion years old, all the way to 15 and beyond, when the universe is only a couple of 100 million years old. When you analyze those fields, you don't just count galaxies, you sort them by redshift, by environments, by mass. Then you watch how the population changes as you move back in time, how filaments that are thick and crowded at redshift 1 turn into thinner threads at redshift 5 and into barely formed structures at redshift 10 or more. In that single pencil beam, you're seeing filaments thicken, clusters swell up, and voids drain out over most of cosmic history. That kind of deep field work is slow and expensive in observing time, but it's exactly what you need if you want to catch the skeleton as it fills in, not just before and after. You get a timeline, not just a snapshot. And that leads to a more detailed question. How smooth or lumpy is this skeleton really when you look at it with every tool you have? One of the sharpest tools for small-scale structure is strong gravitational lensing by quasars. When a massive galaxy or cluster lenses a background quasar, you can get multiple images of that quasar, each taking a slightly different path through the lens. In a perfectly smooth mass distribution, those image brightnesses follow simple patterns. But if there are small dark matter clumps with masses like dwarf galaxies or even lower sprinkled around, they tweak the brightness of individual images. Those tweaks show up as flux ratio anomalies. Dedicated Webb surveys of these lensed quasars can measure those flux ratios to percent-level precision in the infrared, where dust effects are easier to control. That sensitivity lets you probe whether the dark matter distribution is very smooth on small scales, like a fluid, or full of granular substructure. If you see lots of anomalies, you infer lots of small clumps. If you see very few, the skeleton is smoother. That directly attacks one of the big open questions. Is the object holding everything together a clean continuum on small scales, or more like a foam of many tiny halos stuck together? Right now, there's another limitation you have to deal with. Webb is looking at very deep but relatively narrow cones through the universe. Each deep field is like drilling one very thin core sample through cosmic time. That's powerful, but it also means you could get unlucky. You might land your pencil beam on a region that's a bit overdense or underdense compared to the cosmic average. To really know whether too early, too big galaxies and structures are rare special cases or a common feature, you need more volume, more sky. Future Webb campaigns, plus complementary surveys from other space and ground telescopes, are designed to fix that. The idea is to do shallower but much wider maps, covering big patches of sky at moderate depth, and then combine those with the ultra-deep fields. The wide maps give you statistics. How common are early massive galaxies? How often do you find long filaments? How frequently do you see protoclusters at high redshift? The deep pencil beams give you detail, internal structure, and precise histories. When you stack these layers, you literally see 3 different views of the same object. The dark matter map outlines the wells and ridges, the basic gravitational shape. The gas maps show how baryons fill those wells and flow along those ridges. The star formation tracers light up the spots where gas is dense and cold enough to collapse. If the dark matter skeleton shifts, the gas distribution follows. If feedback blows gas out of a region, star formation shuts down, even if the dark matter is still there. Webb gives you the ability to check, region by region, whether that chain holds at high redshift the same way it does nearby. As those surveys continue, the pressure on the theory side ramps up because the data start closing doors. With more deep fields, lensed quasars, cluster maps, and wide area surveys, you begin to pin down the behavior of the glue. If dark matter really behaves like a perfectly cold, collisionless fluid, its fingerprints on small-scale lensing, on halo distributions, and on structure growth across redshift have to line up with what Webb and its partners see. If it doesn't, you're pushed towards warm, self-interacting, or otherwise exotic options, and those options have to pass every single observational test. Dark energy faces the same trap. If it's truly a simple constant, the expansion history must match the observed distance-redshift relation and growth of structure at all times. If it doesn't, then evolving dark energy models or modified gravity get another look, but they're immediately hit with constraints from Webb's early universe data, plus the CMB and local expansion measurements. In other words, the object that holds everything together is getting cornered. You no longer have the freedom to say, it's probably dark matter plus some dark energy, roughly like this. You have to say exactly how smooth or clumpy the dark matter is, exactly how fast structures grow at each epoch, exactly how the expansion rate evolves, and exactly how gravity treats light and matter on different scales. Webb's future surveys, by filling in the skeleton in time and space, are gradually removing the wiggle room. And that sets up the next unavoidable question that this whole story has been pushing you toward. Once the data have narrowed down all the options and you're forced to say what the glue really is, what are you actually talking about when you say the object holding the universe together? So at this point, after all the shocks, you're probably expecting a single dramatic answer, one hidden thing that does all the work. But the truth is sharper and a bit weirder. There is no single object, no giant opaque ball in some corner of the universe holding everything together. What you actually have is a combination of ingredients that, when you zoom out far enough, behave like one coherent connected entity. Dark matter, which provides most of the mass, gravity, which tells that mass how to warp spacetime, spacetime geometry itself, which decides how distances, times, and motions fit together, and dark energy, which controls how fast the whole background is stretching. On human scales, that feels abstract, but on scales of tens of millions, then billions of light years, those ingredients merge into something you can treat as one object, the cosmic web. Dark matter is the mass part of it, the main load-bearing material. It collapses into halos, forms filaments, and sets up the gravitational wells, the dips in the potential landscape, where gas and galaxies collect. Without dark matter, galaxies would have far less mass holding them together, rotation speeds wouldn't make sense, clusters would not stay bound, and the large-scale structure would be much weaker. On its own, though, dark matter doesn't tell you everything because it lives inside a space-time that's doing its own thing. That's where dark energy shows up, not as a local push, but as a kind of boundary condition for the whole universe. It decides how the overall expansion behaves, how fast distant galaxies recede, and how that speed changes over time. On scales of a few megaparsecs or less, gravity from local mass can still overpower that expansion, which is why the Milky Way and Andromeda are heading toward each other. On scales of hundreds of megaparsecs, dark energy dominates, stretching the web as a whole, even as gravity keeps individual nodes and filaments bound. Sitting between those two is gravity itself, described right now by general relativity. Gravity tells you how dark matter and normal matter curve spacetime, and how that curvature guides motion. It tells light how to bend around clusters. It tells gas how to fall into halos. It sets the rules for orbital speeds, for lensing arcs, for the growth of small density bumps into galaxies and clusters over billions of years. If dark matter is the mass and dark energy is the background stretch, gravity is the rule book that says how they combine into curvature. Put them together and you get a fairly clean statement. Dark matter sets up the wells, dark energy stretches the background, gravity translates both into actual geometry. That geometry decides where galaxies can form, how they orbit inside halos, how filaments feed clusters, and how voids empty out. You never see that object directly, but every galaxy image, every cluster lens, every filament map is a partial view of it. Before Webb, you had a fragmented picture of this structure. Galaxy rotation curves shouted, "Extra mass is here." The cosmic microwave background showed tiny temperature ripples that hinted at the seeds of the future Webb. Large-scale surveys mapped out galaxy positions and revealed filaments and voids across hundreds of millions of light-years. Gravitational lensing studies trace mass in clusters and between them. You could already say there is a skeleton and it's made mostly of something dark. Webb tightens all of those threads and pushed them backwards in time. Now you see overmassive galaxies when the universe is a few 100 million years old, which forces you to admit the wells must have formed early and efficiently. You see filaments at high redshift, already feeding quasars and protoclusters. You see chemically enriched gas and active star formation at redshifts 12, 14, even higher, lighting up the structure far earlier than comfortable LCDM predictions. And you see refined dark matter maps and clusters, where Webb's lensing data combined with Hubble sharpen the outlines of the invisible skeleton. It's like the jump from hearing vague secondhand reports about a person to watching that person walk into the room and sit right in front of you. The cosmic web, the thing that holds the universe together on large scales, is no longer just an inference from a few disconnected clues. It's a structure you can see the edges of, measure, and track through time. So when you say James Webb has found the object that holds our universe together, you're not talking about a literal single piece of matter. You're saying that Webb has given you direct, high-resolution evidence of the universe's hidden architecture, a framework of dark matter, shaped by gravity, stretched by dark energy, wrapped in gas and stars, extending for tens of billions of light-years. An architecture that locks galaxies into orbits, lines them up along filaments, and packs them into clusters at the nodes. That object is the universe's architecture itself, the full cosmic web plus the rules that built it. And here's the part that should really get under your skin. You're not outside that structure looking in from a safe distance. You're embedded in it, right now, inside one of its threads. So the next question hits very close to home. If you live inside this thing, what does your own neighborhood of the web actually look like? And what does that say about your future? Right now, while you're sitting here, you're literally inside this thing we've been talking about. You're not watching it from the outside, you're part of one of its threads. Your own Milky Way is not floating alone in some empty void. It's part of a small collection of galaxies called the Local Group, roughly a few megaparsecs across, so a bit under 10 million light-years in size. That group itself sits on a filament of the larger cosmic web, a strand that feeds into bigger structures like the Virgo cluster, and beyond that, the Virgo supercluster and other connected regions spread over hundreds of millions of light-years. On those scales, the Milky Way is just one small halo on one thin strand, and the Sun is just one star in one of its spiral arms. You, personally, are smaller than a speck on a grain of dust in that picture. The positions and motions of the galaxies around you aren't random. The Milky Way and Andromeda are falling toward each other along the local potential well. Dwarf galaxies are orbiting both of them, some getting tidally shredded and leaving stellar streams wrapped around the main halos. Farther out, other groups and clusters are also sliding along filaments, all guided by the same dark matter skeleton. On a map of the local web, your whole galaxy is basically a dot on a line that keeps going far beyond what you can cross in any reasonable time. That raises a blunt question. How does your day-to-day scale compare to the size of the object you're stuck in? Take one of the fastest human-made spacecraft so far, Voyager 1. It's moving at about 17 kilometers per second. That's roughly 61,000 kilometers per hour, or about 38,000 miles per hour, relative to the Sun. That's extremely fast by human standards, but it's painfully slow on cosmic scales. A typical filament feeding into a cluster can be a few megaparsecs across, say 3 megaparsecs, which is about 10 million light-years. 1 light-year is about 9.46 trillion kilometers. Roughly 5.88 trillion miles. So you're talking on the order of 10 million times that distance. If you tried to cross even that single filament at Voyager speed, you'd need time far, far longer than the current age of the universe, which is about 13.8 billion years. You are not traversing this structure, ever. No rocket you can build under normal physics is going to carry you from one side of the cosmic web to the other. The object that holds you is, for all practical purposes, uncrossable by direct travel. But you don't need to cross it to know it's there. You have something better: instruments that turn tiny signals into a global map, and Webb is one of the sharpest of those instruments. Webb is, in a very literal sense, an extra sense organ bolted onto your species. Your eyes see a narrow slice of wavelengths over a few kilometers. Webb sees from about 0.6 to 28 micrometers in infrared across distances of more than 13.5 billion light-years of lookback time. It extends your reach both in wavelength and in time. When you look at Webb data, you're seeing the skeleton forming when the universe was a few 100 million years old. You're seeing galaxies snapping into the wells of the dark matter. You're seeing gas streaming along filaments, and clusters condensing at nodes that will later grow into massive structures. Through Webb, you can watch the object at multiple stages: thin and tentative at high redshift, thicker and more complex at intermediate times, and fully developed in the nearby universe, all in one coherent framework. It lets you test whether your theoretical skeleton matches the real one by comparing the model to what the telescope actually records. In that way, Webb is like a nervous system connection between your little planet and the larger web you're embedded in. It feeds back information about the state of the structure you live inside. And this is where the stakes stop being abstract and turn into something much more direct, because if the nature of this object changes, everything down the chain changes with it. If dark matter turns out not to be cold and collisionless but something stranger, then the way halos merge, how quickly filaments form, how galaxies grow, all shift. That affects when and where stars form, how many black holes grow to huge sizes, and how often galaxies crash together. If dark energy isn't a simple constant, if it evolves with time or changes behavior at some epoch, then the large-scale stretching of the web changes. Filaments might eventually thin out more than you expect. Clusters might stop growing earlier. Or, in some scenarios, everything bound today might be torn apart in a distant Big Rip phase. If gravity itself deviates even slightly from Einstein's equations on the largest scales, then your interpretation of every lensing map, every cluster mass, every growth curve of structure has to be redone. The web you thought you understood might be denser, lighter, more flexible, or more rigid than your current model says. That feeds all the way down to predictions about how many stars form over cosmic time, how many supernovae explode, how quickly elements like carbon and oxygen spread, and how many planetary systems ever get a stable window long enough to host life. Even the final fate of the universe, whether you head toward a slow heat death where everything cools down and fades, a violent big rip that tears structures apart, or some more exotic loop or collapse, depends on the true nature of this invisible framework. The way the object that holds the universe together behaves today sets the boundary conditions for what happens trillions of years from now. Webb is your first clear, high-resolution look at that framework at the moment it was locking into place. It doesn't answer everything, but it changes the conversation. You're no longer guessing in the dark. You're seeing where the standard model bends, where it holds, and where it might break. And you're doing that while sitting on one tiny rock in one modest galaxy, on one thin strand of a structure that runs far beyond anything you'll ever travel. So the real takeaway is simple and a little unsettling. You live inside the object that holds the universe together. You can't escape it, you can barely move across it, but you can, with the right telescope, finally start to understand what it actually is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.